Okay guys, Timmy coming at you here again, and today what I'd like to do is I'd like to explain to you the four pressures that affect capillary fluid volume. Now remember, the only place that nutrients and gases are exchanged is at the level of the capillary, right? And fluid too. So let's look at this for a minute. Remember, if you recall, I talked about the fact that the left ventricle develops systolic blood pressure. So in the systemic arteries, when the left ventricle contracts, that blood that's going through the arteries is under pressure. That's at systolic blood pressure. And we know that as that blood moves away from the left ventricle down to the level of the cell, that the pressure, the systolic blood pressure, decreases, right? You don't want a pressure of 130 millimeters of mercury at the level of the capillary, because capillaries are one cell membrane thick. So those capillaries will be popping and you'll end up with a stroke or a grabber or all kinds of bad stuff when you want to talk about. So what I'm going to do now is I'm going to explain to you how fluid moves into and out of the capillary and how different pressures affect that. So here we go again. We saw this, right? We know that the arterial blood is under pressure, right? And here's the arterial end of the capillary, and then the venous end of the capillary, and then of course you got your cell. And then we know that the space between the cell and the capillary is called the interstitial space. And we know in the arterial end of the capillary that it's under pressure. And what determines that to a large degree is one of two things. It's either systolic blood pressure. The other thing that has a profound effect on it, even in normal physiology, is gravity, right? And that's important to understand because that has a lot of clinical impact. So knowing that fluid is going to be moving in and out of the capillary, now what I want to do is explain to you the different fluid pressures and how those different fluid pressures affect fluid volume, capillary fluid volume. Now look, the first pressure that we're going to talk about is called capillary fluid pressure, or in your book, it's called hydrostatic pressure. And hydrostatic pressure is the pressure of the plasma of the blood against the capillary wall. And it tends to force fluid out of the capillary and into the interstitial space. So let's see. Here you got a capillary. Remember, you got fluid in your blood. You don't bleed dust, right? So there's water in there, fluid, right? And capillary fluid pressure is the pressure of the blood against the capillary wall, and it tends to force fluid out of the capillary. That's capillary fluid pressure. Now, if you recall, when we talked about low sodium and it being a bad problem because the central nervous system doesn't have a lymphatic system. So, excuse me, fluid pressures, fluid shifts into the central nervous system can be really bad for you. But for the most part, wherever you have arteries and veins, you have lymphatic vessels. And one of the function of lymphatic vessels is to drain excess fluid from the interstitial space and bring it back to the heart, the right side of the heart. So in a lot of respects, lymph vessels are similar to veins. So capillary fluid pressure, which is to a large degree determined by your systolic blood pressure. And the other thing that determines it is gravity. Now think about it. Just hold a bottle of pop-up, right? That's half, you drank half of it. The fluid isn't up at the top, it's at the bottom, right? By virtue of gravity. So capillary fluid pressure is greater in the legs than it would be in your head, right? Because most people, depending on their profession, are upright during the day. So capillary fluid pressure is always going to be greater in your feet. So what that means is that more fluid is going to get pushed out of the capillary and into the interstitial space. And I'll explain that more in a little bit. Now, your second pressure is there's pressure in the interstitial space, right? And that pressure pushes against the capillary wall, and it tends to force fluid from the interstitial space back into the capillary. So observe. Whoops, sorry about that. So interstitial fluid pressure is the pressure of fluid in the interstitial space, and it tends to force fluid back into the capillary. Now, capillary fluid pressure, what does it do? It tends to force fluid out of the capillary and into the interstitial space. So if these were the only two fluid pressures that were operating, then capillary fluid pressure in normal physiology is always greater than interstitial fluid pressure. So fluid, water, would begin to collect in the interstitial space. But that's not the only fluid pressure. The next fluid pressure is what's called capillary osmotic pressure. So that, again, that's why I spent so much time on test number 1 and test number 2, is because all that stuff that we talk about is going to come back and haunt you. And here we go. Right? I explained to you that sodium and albumin in normal physiology determine capillary osmotic pressure. Why? Because albumin's so big it's only found in the blood, and sodium is always highly concentrated in the blood. And if you remember that osmotic pressure is the ability of stuff to draw water towards it by osmosis. So when you have sodium and albumin in the blood, it's going to draw water from the interstitial space back into the blood by osmosis. That's the osmotic effect of sodium and albumin. So that's pressure number 3. Pressure number 4 is what's called interstitial osmotic pressure. So there are small proteins, typically that have escaped the cardiovascular system and end up in the interstitial space. So these small proteins, and if you also remember, I told you it's not the size, it's the number. That's why sodium can draw just as much water towards it as the giant protein albumin. So it's not the size, it's the number. So these small proteins in the interstitial space, they tend to draw water out of the capillary and into the interstitial space by osmosis. Right? Remember, if stuff can't move, water can always move. Now, if you take those 4 pressures, if you take capillary hydrostatic pressure or capillary fluid pressure, interstitial fluid pressure, capillary osmotic pressure, and interstitial osmotic pressure, if you add those 4 up, depending on where water would move, if you add those 4 pressures up, the net movement, meaning after you've included all the effects of all 4 pressures, the net movement of fluid in normal physiology is out of the capillary. So the question is, why don't you have big bags of fluid on your legs or arms, or you got a big swollen head? Well, the answer is that you have a lymphatic system. And when excess fluid begins to build up, the lymphatic system will take that excess fluid, and all lymph vessels drain into, just like veins, the right side of the heart. So any excess fluid that accumulates in the interstitial space is typically removed by the lymphatic system. Now, lymph vessels are very similar to veins. We learned that veins have no pressure, that how do you get venous blood back to the heart? Contraction and relaxation of skeletal muscle and the one-way valves. Well, lymph vessels are very similar. There's no pressure. They have one-way valves, and they return lymph, which is basically the plasma of the blood, minus the big stuff, back to the right side of the heart. Now, look. Let's say, for example, that you are standing at a job, right? You're doing some line work, right? At a factory. And you're standing. You're not contracting your muscles a lot. You're standing. Well, what's going to happen? Well, let's look. What's going to happen is, by virtue of gravity, is capillary fluid pressure is going to increase. Why? Because you're not getting that venous blood back to the heart because you're not contracting and relaxing your muscles. So capillary fluid pressure is going to increase. It's going to force more fluid out of the capillary. Now, what happens is the lymph vessels, they take that excess fluid typically and bring it back to the right side of the heart, right? They take that excess water and bring it back to the right side of the heart. But lymph vessels kind of work like veins too. That how do you get lymph fluid back to the heart? Contraction and relaxation of skeletal muscles and one-way valves. But if you're not moving, not only are you not moving the venous blood, so the capillary fluid pressure is going to increase, but you're not moving, so you're not getting that lymph vessels contracting and bringing that lymph fluid back to the heart. So what happens? You get edema, right? You get swelling. So watch. What does a doctor tell you if you got swollen feet? To get off your feet and elevate your feet above the level of your heart. So if you do that, gravity will take over and it will reduce capillary fluid pressure, right? It will decrease capillary fluid pressure, and it gets venous blood and lymph fluid back to the heart. As a result, the swelling goes down. So those are the 4 fluids that affect cardiovascular fluid volume. And it also explains why some people, especially if they've been standing for a long period of time or sitting on a long plane ride, like maybe a plane ride from Milwaukee to, I don't know, maybe Waukegan. Typically, transcontinental plane flights, they make you get up every couple of hours, right? Because we also talked about the fact that if venous blood doesn't move, it tends to clot. Arterial blood is always moving because it's under pressure. It's under the pressure that's developed by the left ventricle. So those are the 4 pressures that affect capillary fluid volume. And I hope that helped. Oh, I'm going to start saying this now too. If you like this video, give it a thumbs up and also subscribe to my channel. I can't make any money off of this, not like I actually would, but somebody told me to say that. I don't know why.